So there we go. Okay, so let's do a little bit of recap of what we were trying to do, and that was to look for solutions to Einstein equation. I'll not go back all the way to right in the beginning. Also should mention that I am on phone network. Institute network is down completely. So if there is a
Sorry, your
issue with
voice is cracking.
okay, so I don't know what to do. Recording. Okay, so we were looking at solutions to Einstein equation, and as I said, I'll not go back all the way to the beginning of this discussion, but what we did was that if we are looking at simple solutions with large amount of symmetry, then those kind of solutions have the property that the Ricci scalar for those kind of solutions is constant, and a Ricci tensor is proportional to the metric of the space times, of course, the Ricci scalar. And Riemann tensor can be written in terms of products of the metric components. Okay, these kind of spaces are called maximally symmetric spaces, and these maximally symmetric spaces have d into d plus 1 by 2 number of isometries. That is the largest number of isometries that any space could have in the space dimensions. Okay, we looked at these kind of spaces by just looking at the number of killing vectors that a space could support, and the maximum number of killing vectors are the ones which are d into d plus 1 by 2, of which if you are looking at Euclidean space, then of which d of them are translation local translational killing vectors, and d into d minus 1 by 2 of them are local rotational killing vectors. And if you take both of them into account, then that is the one which gives you maximally symmetric space. Then we also looked at how to construct maximally symmetric space. So it's still a recap, and that is to start with one higher dimensional flat space, and in the one higher dimensional flat space, you write down a metric which is written in terms of constant d by d matrix C alpha beta and a constant parameter k. And because both C alpha beta and k are constant, the Riemann-Christoffel connection would vanish, simply because that involves derivatives of the metric with respect to some coordinate. But since the metric components are independent of coordinates, the connection vanishes. And since connection vanishes, its derivative also would vanish, because the metric is independent of coordinates, and therefore the curvature is also zero. So that is why d plus 1 dimensional space is flat. But in that flat d plus 1 dimensional space, we embed a quadratic equation, quadratic surface. Typically, it's called a quadric actually. And you take a quadric written in this particular form, k times c alpha beta x alpha x beta plus z squared equals 1, and ask what is the induced metric on this surface, starting from this metric c alpha beta dx alpha dx beta plus k inverse dz squared. Okay, so one way to do that is to just eliminate z from using this equation. Yes.
Yes, sir. I mean, in a flat space time, is it necessary that C alpha beta has to be a constant?
No, it doesn't have to be. Like,
So,
for
I
example,
mean,
in
you are just...
yeah.
Okay.
Like, for example, you take Minkowski space and you do some horrible coordinate transformation, the metric components are not constant. Okay. Right. So with respect to some new coordinates, the metric components could be very, very complicated. Okay. But hello. Can you hear me?
Yes, sir.
Yeah. So if you take Minkowski space and do very complicated coordinate transformation, the new metric will not be constant metric. Okay. So it is not necessary to take constant metric, but the fact that the new complicated metric in the on the Minkowski space still describes the
Yeah,
flat space, okay, is the important aspect, right? So there exists one frame in which you can make the metric look take the form in which the metric components are independent of coordinates. Okay,
yeah, yeah. Okay.
so this is purely for convenience. If one wants to make one's kind of computation more complicated and much more general, then of course you could work with arbitrary metric whose all curvature components are zero, and the results wouldn't change. They would still give you the same result. Okay, but the whole idea of general coordinate invariance is to say that, like, even if you have a metric which is very, very complicated, uh, and that metric has a property that all Riemann tensor components are zero, then that metric should be obtainable, can be kind of brought into a form in which most of the metric components are constant. Okay. Uh, in fact, most probably all of them are constant kind of stuff. So that is what we want to utilize, because we want to kind of simplify our computation, and that is the reason for choosing this. Okay. Is that okay? Okay. Fine. So let's get back to this one, and we have this metric on the uh, D plus one dimensional space in which a quadratic surface is embedded. Okay, and also I should say one thing, that, like, this quadratic surface thing is simpler if we choose k's and c's to be constant. If we did not take k's and c's to be constant, then to call the surface to be a quadratic surface is a bit tricky, because these could be functions of coordinates. Okay, so but of course, you can embed sphere in flat three-dimensional space written in terms of x, y, z, and it looks kind of simple quadratic equation. But if you write it in terms of say r theta phi, then it looks like a linear equation, right? Because you just say r is equal to r naught, where r naught is the radius of the sphere, and so on. So depending upon what choice of coordinate system that you take, the equations can take different forms actually. Okay, but the quadratic form of the equation is quite suitable for dealing with the problem that we are kind of handling right now. Okay. Fine. So what we want to do is to ask, what is the induced metric on the surface defined by this equation. Okay. This equation is the equation of a sphere if C alpha beta is a metric on a Euclidean space. Okay. If C alpha beta has a Lorentzian signature, then of course it's not a sphere, because one of the components, at least one of the components, would have had a negative sign. Okay, so of course we are tacitly assuming that this is Euclidean. Okay, so elimination of this just means that you write down z in terms of these, and then that allows you to write dz in terms of dx alphas, and you can eliminate dz squared in this equation, and that gives you a metric which looks like this. Okay, of course it can be further simplified by pulling out some terms, and you can write down g alpha beta in this particular form. Okay, so as I said last time, that I should have actually written down some other variables. I should have written down c alpha sigma dx sigma dx alpha dx or whatever, something like that. But I just didn't get time to do that. But I'll correct it next time. Okay. But anyway, this expression is correct. Okay. This expression is a bit sloppy, simply because I should have really written down c alpha sigma x sigma dx alpha times c beta rho x rho dx beta. That's what I should have really written down. Okay, so if k is equal to 0, then you actually end up with a flat space that just corresponds to fixing the z value in this coordinate space to be some fixed number. Okay, and just forget about this piece and you get this metric. That is clear from this equation that if you set k equal to 0, then z is equal to some fixed number, and you just kind of, if z is equal to fixed number, then dz is 0. So this piece becomes 0 by 0, but there's nothing to worry about that. You can kind of use L'Hopital rule to see that it just goes away and you get this metric. Okay, that is a flat space. Okay, so you get g alpha beta is equal to c alpha beta. Okay, fine. In this particular case, d into d plus 1 by 2 isometries correspond to the d plus 1 dimensional, corresponds to the symmetries which are inherited from d plus 1 dimensional space, and those corresponds to these transformations that that one can look at, which corresponds to rotations in d plus 1 dimensional space. Okay, fine. So if you demand that the metric is invariant under the d plus 1 dimensional transformations, then one gets equations of this kind, which just follows by saying that if you do this coordinate transformation and demand that the metric is invariant, you would get these equations. Okay, that alpha beta, c alpha beta, and is related to c prime gamma delta. The component involving alpha and z type of thing continues to be 0. The one involving z gives you some k inverse kind of quantity. Okay, so we can make various choices between these to show that some of these rotational transformations correspond to the symmetries of the embedded space given by the quadratic equation. Okay, so for example, if you say that k is equal to k prime and c prime is related to c in this particular fashion, then you can show that these transformation corresponds to rigid rotations. Okay, fine. On the other hand, if you look at something quite complicated like this, that r alpha z is equal to a alpha and r z alpha is equal to some complicated function written in this form, okay, and r z z is equal to this quantity, then you can check that this corresponds to translation. Okay, there are these such parameters, and those are the translation isometries. Okay, so you get d-dimensional rotational isometries by choosing the transformation to be this, and d-dimensional translation isometry by choosing the transformation which is like this. Okay, so as you can see that the translation, which was a very simple transformation on the space itself, in the embedding space, that looks like quite a complicated object. Okay, but nevertheless, it is still a kind of symmetry. Okay, fine. So we kind of carried out this computation by doing a transformation of all these, plug that in the equations for r alpha gamma, r alpha z, and r z z. Okay, using all these fellows, and you can kind of determine the quantity, one of the quantities which are defined here, which is a quantity b. Okay, you can determine that by demanding that the off diagonal component of the metric continues to be 0. Okay, so this equation and all other equations can kind of basically impose additional constraints on the quantities, but this is the one which will tell you what you would really need. Okay, and that tells you what b is. Okay, and you can determine b in terms of a's. Okay, so then there was this exercise which is basically what I was trying to tell you, that if you take this transformation, then that corresponds to translation, and that exercise corresponds to the following statement, that if you are at the origin, okay, then this transformation, which is what what we are looking at. Can you hear me? Hello?
Yes, sir.
Okay.
Yes, sir.
Okay, because it said yeah, the connection is unstable.
Hello.
That's why I asked. Hello? I can hear you. Okay?
Yeah, your voice is getting cut actually.
Yeah, because it said the network is unstable. So I suspected that. Okay. I hope it is a little better now. So these two transformations together basically gives us d into d plus 1 by 2 isometries. Okay. So so that is how we kind of obtain the solutions by embedding quadratic hypersurfaces in one extra dimension. Okay. Fine. So there were some exercises that I had given, and one of them was that you choose the metric G alpha beta is equal to C alpha beta plus K upon 1 minus K C gamma delta X gamma times C alpha sigma X sigma C beta rho X rho. Choose the metric components to be this and show that the Riemann-Christoffel connection is just K times X alpha G beta gamma. Okay. Now this is very useful because it tells you that gamma is proportional to G, and therefore if you take covariant derivative of gamma, then that derivative only acts on X, because whenever it acts on G, G is covariantly constant. So life can become simpler by using the form of gamma to be of this kind. Okay. So that is one useful thing. But once you derive this, you can derive geodesic equation. Given that this equation G is linear in X, you should be able to solve it. Okay. And you can, given that gamma is of this form, you can try to check whether the Riemann tensor that can be obtained by computing it using this gamma takes the form of this kind. Okay. Fine. So yeah, so let me skip this part because we have done this, that if you take the Euclidean signature, you can show that this matrix reduces to a metric which is of this form. For k greater than 0, it is a metric on the sphere. For k less than 0, it's a metric on some hyperbolites. Okay, so which is what we had done earlier. Okay, and yeah, so let me just skip this part because this is just an example that we can work out. Okay, fine. So so instead of taking this quantity to be 1 minus x dot, sorry, 1 minus x dot x piece, if you take 1 plus x dot x piece, okay, then in that case you would get an equation which is you get a metric which is a little different, and in that case you could do a coordinate transformation and bring the metric into a form which is like this. Okay, there are two different ways of writing this metric. One is this one, and the other is this one. Okay, and this has explicit time dependence with exponentially growing scale factor of the spatial part of the metric, and this is what is called the de Sitter metric. Okay, and the de Sitter metric, of course, can be written in the time independent form. This is explicitly time dependent metric. Okay, but you can write this in the time independent form by doing a coordinate transformation, and here is a time independent form of the metric. Okay, uh, so so in the double prime coordinate system, you do not see metric component have any explicit time dependence. Okay, but nevertheless, it is the same de Sitter metric that we are looking at. Okay, fine. So The next thing that we looked at was spherically or maximally symmetric subspaces, and one of them was a spherically symmetric space, and uh, in that case, we we could kind of reduce the metric to a form where spherical symmetry tells us that the metric components would be of functions only of r and t, but not functions of theta and phi, except of course the metric on the sphere, which has a very specific sin squared theta dependence. Okay, but all other GTT, GRT, GRR, and G are functions of only r and t. And if we also demand that the space is homogeneous, then you could kind of show that the off-diagonal component GRT can be set to 0, because homogeneity would tell you that you cannot kind of have this component non-vanishing. Okay, just give me a minute. I'll be back in a moment. Okay, so so as I was saying was that if you have homogeneity, then you can show that GRT component of the metric should also vanish. And besides that, homogeneity means translation invariance, and therefore it would also tell you that the metric should be independent of the radial coordinate r. Okay, so that basically reduces the metric components to be only functions of time. Okay. Okay, so then of course you have another thing that you could do, that given that this is only function of time, GTT is only function of time, you can always do reparameterize time and soak up the GTT as a function of time into the new reparameterized time to make this component become just one. Okay, that would require us to write t prime is equal to some complicated function of t, such that dt prime is equal to gtt square root of gtt times dt. Okay, whatever is that function, it doesn't really matter as long as we can do that transformation. They would transform all these functions into functions of t prime, but putting primes on that makes no difference. Therefore, we will just assume that the new coordinates are just coordinates t, coordinate t, and we just set GT2 equal to 1. And in the end, we get a metric which would take the form which is of this kind. Okay, and okay, so the spherical symmetry of the subspace basically tells us that we could write down the metric in this particular form for the spatial part, and you can choose polar coordinate system to write down the metric in this form. Okay, so this is the famous Robertson-Walker metric. Okay, fine. So now let's come to a new set of solutions which require us to have a source which generates the gravitational field. Okay, and we will now consider a point source. Okay, that is the simplest thing that we could consider. Okay, and if you have a point mass, then like for example, suppose you are thinking of, say, sun producing gravitational field, then if you are very far away from the sun, by very far away I mean that the radius of the sun is much smaller than the distance between the observer and the sun, then it, to a good approximation, considering sun as a point particle, is a valid thing to do. Okay. On the other hand, if your distance from the sun is comparable to the radius of the sun, maybe just the order of magnitude larger than the radius of the sun, then it may not be such a good approximation. In that case, you may have to kind of take the finite size of the mass into account. Okay, so what we are going to do is to basically not worry about that detail. We'll assume that we are reasonably far away from the point source which is generating gravitational field, and we will actually replace that point point source by a delta function, okay, which actually does ignore the size of the object. Okay, fine. So if you have a source, then you are of course not solving the vacuum Einstein equation, which is vacuum Einstein equation was R alpha beta minus half G alpha beta R is equal to 0. That's not what we are going to solve, but we are going to solve this equation as R alpha beta minus half G alpha beta R is equal to T alpha beta, and T alpha beta is generated by this delta function source. Okay, fine. Now the question is, how do we go about solving a problem which involves a delta function source? Okay, and the idea is something which is familiar to us. It's not like we are doing something new. It's something we have done in electrostatics, and that is that you have a point charge producing electric field, and what you do is that uh, barring the place where the point charge is sitting, all other uh, region around it, in the entire space around the point charge, is free of the electric charge. Okay, so therefore, what we do is that we say that we are going to solve the equation for electrostatic problem in the space where there is no point charge. Okay, so we remove the location of point charge from our calculation, solve the problem. Okay, and then you reinstate the point charge and determine the constants of integration in the equation. Okay, so this idea is, of course, requires us to utilize certain aspects which are coming from the point source, and that is the symmetry of the problem. Okay, if you didn't have a point source at all, then your space would have had translational invariance in all directions. Okay, and of course rotational invariance locally. But if you have a point charge, then it fixes a particular point in space, a place where the charge particle is. Okay, and only symmetry that you have is rotation about that point. Okay, so if you put that point to be at origin, then the rotation about that origin is the only symmetry that you have, but you cannot translate because putting a charge at a particular point has broken the translational invariance. Okay, so what we will do is to solve the electrostatic equation by assuming only spherical symmetry about a point, but not use translational invariance. So if you do that, then our equation, which would have looked like this, uh, which is a Poisson equation, that the Laplacian acting on the electrostatic potential is equal to the charge times the delta function, because we are taking point charge. Okay, we will solve this problem by using spherical symmetry, but ignoring the source, and solve the Laplacian acting on phi is equal to 0. Okay, we will solve this equation everywhere in three-dimensional space except at x equals 0, the place where the charge is. Okay, and that is a valid thing to do simply because delta function is 0 everywhere else except at x equals 0. So therefore, this is what we will get if we try to solve it at any other spatial point. Okay, fine. Only thing that we need to take care of is the symmetry dictated by the source, and that is a spherical symmetry, and therefore we should seek a solution which has spherical symmetry. Fine. Now, this is something you must have done, solving Laplacian Laplace equation in flat space using spherical polar coordinate system, and the solution is actually phi is equal to some constant by r. Okay, you can check that. You can write down this as 1 over r square del r square del r plus some angular part. Since our solution is spherically symmetric, it has no angular dependence, so the angular part of the Laplacian gives you 0, and 1 over r square del r square del r is solved by some constant by r. Okay, it's just a few line calculation actually, really one line. Okay, fine. So of course this solution is valid everywhere except at r equals 0, because r equals 0 is the place where the point charge is sitting, and therefore we cannot say that phi would take this value, and of course phi itself would be diverging at that point. But what we will do is we will use the fact that the charge particle is sitting at origin to determine this constant. Okay, so that is done by using Gauss law. Okay, so let's do that. Okay, so what we will get is that this solution to the Laplace equation gives us the electric flux to be minus gradient of that solution, which is C upon R squared, pointing in the radial direction. So using Gauss's law, we know that integral of this electric field over the surface, uh, which is covering the, which is enclosing the point charge, would give you 4 pi times the total charge actually. Okay, so in this particular case, we have this solution. When you do an integral, you get R squared cancels out, C pops out of the integral, it's a constant, and integral over a sphere gives you 4 pi. So you get the answer 4 pi C from Gauss's law using our solution. Okay. On the other hand, Gauss law would tell us that if you have the charge enclosed in it, then this integral would have given you the total charge enclosed inside the surface. So therefore, 4 pi C should be Q, and therefore C is Q upon 4 pi, and this is our solution. Okay. So the trick here is to not worry about the point source, but uh, uh, but use the point source to find out what is should be the symmetry of the solution. Then look at the solution respecting that symmetry and compare that with the source to fix all the constants of integration that you would get. Okay, and here is the solution. Okay, fine. So we are going to follow the same strategy for the point mass for the Einstein equation. Okay. So then our life is simpler because just a few minutes ago I said that like we are not solving vacuum Einstein equation because it should be R R alpha beta minus half G alpha beta R is equal to T alpha beta. But since T alpha beta has a delta function dependence, okay, we could solve Einstein equation everywhere else by setting T alpha beta to 0 and use the delta function at the end of our calculation. Okay, so that makes our life much simpler. Our problem actually becomes R alpha beta minus half G alpha beta R equals 0, which of course we know can be reduced to R alpha beta equals 0. Okay, in case if you don't remember, all you need to do is to contract this equation with G alpha beta, or rather G alpha beta with contravariant indices. That gives you R here, and that gives you D by 2 times R here is equal to 0. Okay, and if you get that equals 0, if D is not equal to 2, then it tells you that the Ricci scalar is 0. If you set Ricci scalar equals 0, then it tells you that R alpha beta should be equal to 0. That's how this equation appears. Okay, fine. So, coming back to the problem, although we have ignored the delta function, we know that the delta function source would have spherical symmetry. So what we will do is start with an arbitrary metric and utilize the fact that the problem should actually have spherical symmetry. Okay, fine. Now, besides having the spherical symmetry, we are also going to assume that the point source that we are considering is time independent. Okay, that means that source has some mass, and that mass is fixed. Okay. Now, most of the realistic situation, like for example, if you think about sun, or if you think about any other star or galaxy as source, then its mass is not constant actually, because it is soaking up some stuff from the interstitial space, or it is also radiating a lot of light out and so on. So these are all time dependent objects. Okay, but the change, the fractional change in the mass of these objects is very small compared to uh, the absolute mass of the object, and therefore to large extent this assumption is reasonable. Okay, now of course if you want to do a more accurate and realistic computation, one of course needs to do uh, more detailed computation. So there exist branches in astrophysics where you do scalar studies, and stuff like that, in which you need to do more detailed you need to have more detailed understanding as to how you deal with the evolution of a star, for example. Okay, but let's not worry about that right now. Okay, so so what we are going to do, therefore, is that we are going to utilize two symmetries. One is the spherical symmetry of the problem. This is, of course, spatial aspect of the symmetry, and time independence of the source, which will tell us that the solution, that the metric components that we would write down would be time independent. Okay, so now, given the fact that these are two symmetries, we have already studied that these symmetries should be there no matter, you know, how you write down the metric. By that I mean you could write down the metric in any particular form. These symmetries should be there. All you need to do is to find out what corresponding Killing vectors. Okay, but in order to obtain a solution to Einstein's equation, it is better or it is more convenient to write down the metric which has these symmetries kind of manifest. Okay, so that uh, you don't have to look for Killing vectors for a complicated metric solution and then check that the final solution that we have obtained actually does have the symmetries that we mentioned above. Okay, fine. So yeah, there's a typo here. That's what I was saying, that if the coordinates are not good, the symmetry may not be manifest, but uh, let's not do that. Okay, fine. Now, so one thing is that, like, if you have spherical symmetry, this is something we have studied in quantum mechanics, that if the problem has spherical symmetry, then the potential should be independent of r vector. It can depend on the magnitude of r, but not on the vector quantity. Okay. So similarly, if the solution is spherically symmetric, then metric should not depend on x vector or dx vector, but it can depend on the dot products of these quantities. Okay, so the allowed quantities, therefore, are quantities like x dot dx or dx dot dx, or of course x dot x. Okay, so we are going to write down x dot x to be r squared. So therefore, r is equal to square root of x dot x is a quantity that is one of them, and metric can contain factors which are like this. So that tells us that that the possible metric that you could write down is g1 of r dt squared plus g2 of r times dt times x dot dx plus g3 times dx dot dx plus g4 times x dot dx whole squared. Okay, everything has to have a double differential, and that each one of them has. Okay, so this metric would respect the spherical symmetry. Okay, but this is not good enough, because although metric components are written as functions of r, the metric line elements are not very convenient objects. Okay, although they do respect spherical symmetry, they are not written in the proper spherical coordinate system. Okay, fine. Now, besides looking for a solution which is stationary, a stationary solution is the one which is independent uh, of time. There is no explicit time dependence. Okay, which is what we have. There is no explicit time dependence on any of these metric components. What we would want to do is to look for a solution which is actually static. Okay, so we would like to do that. Okay, so if you are looking at a static solution, then we would like to ensure that there is no component like this, which is dt with anything else. Okay, dt times say dx or dt times dr or whatever. Okay, so let us first bring this metric into a spherically symmetric form, and then try to kind of get rid of a piece like this. Okay, so that we know how to do. Spherical polar coordinate system allows us to write x1, x2, x3 in this particular form, and that tells you that dx dot dx is r squared dr squared plus r squared times the metric on the sphere, whereas x dot dx can be written as d of x dot x. Okay, half of d of x dot x. But x dot x is r squared, so therefore d of r squared is r dr. Okay, so this factor of half goes away because it could have been 2r dr, but there's a half which removes it. Okay, so this allows us to replace dx dot dx and x dot dx in terms of dr. Okay, and of course d theta and d phi. So that reduces our metric to a form of this type. Okay, the time part is unaffected. And dt times x dot dx becomes r times dr times dt. The function is as it is. Dr squared has two contributions coming from just a hello, hello,
Yeah,
yeah. I'm sorry, got a call from somebody. Okay, so coming back to this, so we get a contribution for dr squared from two terms. One is this piece, dx dot dx gives us dr squared, okay, and there is another piece which is x dot dx whole squared also gives us dr squared because it will give you r squared dr squared piece, okay. So you can collect that and you get g3 plus r squared times g4 dr squared, and then dx dot dx gives you a piece which is like this. Okay, so this is how the metric would look like if you are working in spherical polar coordinate system. Okay, and as I said that we would like to look for a solution which is static, and that can be done by making yet another change of variables, and that is to write down a new coordinate, time coordinate, which is t prime, which is t minus some function of r, such that dt prime is equal to dt times df by dr. I should have written df by dr really, because it's a function only of r times dr. Okay, and if you kind of plug that in, you get terms which involves dt prime by dr piece uh, in both places, and then you get a dr squared piece, whole thing coming from dr squared. And what all you need to do is to find out, to set the off diagonal piece to 0 to determine what this function should be. Okay, so so it tells us that we should look for 2 times df by dr uh, is times g1 is equal to r times g2. If you set that equation and solve it, it will tell you what should be this coordinate transformation, which should get rid of the off diagonal piece. Okay. Once you do that, then you have a metric which is not only spherically symmetric but static. Okay, not just stationary but static, because there is no cross time dependence with the spatial dependence. Okay, so this is what this equation is. Okay, that minus 2 times this plus r times g2 is equal to 0. You can solve this by writing this integral expression. Okay, but once you do that, then you can write, you need to plug that back in, because df by dr appears at various other places in the equation. Uh, this should have been squared actually. I'm sorry for that. Uh, correct it. Okay, so df by dr appears here and here, but that is not bad, because although f is written in terms of integral, df by dr is a reasonable function that one could use, and plug that in to write down the final expression, which is like this. Okay. Now at this point, this still looks very complicated, but you know, there is nothing very sacred about G1, G2, G3, and so on. They are all functions of R. So all we can do is to kind of rewrite these functions as whatever we want. Okay. But what is more important is that you notice that all components of the metric are only functions of the radial variable. Okay, so this horrendous looking object sitting in front of dr squared can be just simplified by just saying that this quantity times dr squared is equal to dr prime squared. Okay, whatever is that dr prime, then integrating that quantity will tell you how r and r prime are related. Okay, hello, hello.
Yes, sir.
Okay, good, good. Because it again stays unstable. That's why I was worried. Okay, so you substitute this whole expression as dr prime squared, and of course you have to solve some complicated object. Write down r prime in terms of r as some weird function. It doesn't matter. You replace all these fellows by r prime. Okay, fine. So you can do that and simplify the expression. The other possibility that you could do is to take this entire expression, g3 times r squared, and replace that by some other quantity r prime squared, or what I have called rho squared. And that has an advantage compared to the first transformation, is to ensure that the spherical metric is simply defined as radial part squared times the sphere metric. Okay, so instead of redefining this quantity, what we will do is redefine this quantity. Okay, so we will do this. We write down rho squared is equal to g3 times r squared, and then replace everything else in terms of rho. Okay, now that is kind of easy. Wherever you have r, any function of r, you replace that as a function of rho. Okay, so whatever is this function, we will know how to write that as a function of rho. Okay, so we will just redefine them to be g1 of r is equal to a of rho, and uh, and similarly this complicated object is equal to b of rho and stuff like that. Okay, fine. So if you do this, it will tell you how to relate a of rho to g1, and that is uh, by looking at this redefinition. So del g1 by del r times dr is equal to del a rho by del rho times d rho. Okay, so it tells you how dr and d rho are related. Use that, plug it in here. This function written as rho times this square of this object can be redefined as a new object. Okay, so what we'll do is this entire function, let me go back again, everything in this parenthesis, okay, is here. This quantity squared is sitting here times d rho squared is equal to dr squared times this quantity. So we define that as some another function b of rho times d rho squared. Okay, at the end of all this coordinate transformations and redefinitions, your final metric takes a form which is like this. Okay, and so what we find is that, like, although we initially started off with 4 functions, we are really reduced to only 2 functions to be defined, and those 2 functions are only functions of radial variables, uh, and therefore we should be really solving some kind of ordinary differential equation, because it is we are solving for functions which are functions of only single unknown. Okay, fine. Now, of course, by appealing to the symmetries, we could have written down this metric right in the beginning, okay, without doing all this complicated stuff. But it is good to know that even if we had written down the metric in a kind of complicated and a wrong choice of coordinate system, there is a systematic way of obtaining the metric in a simplest possible form by uh, doing coordinate transformation in a step-by-step fashion. Okay, so that is how we arrived at this equation. Okay, fine. So is this fine? Any questions? Aman?
Yeah, it's fine.
It's fine. Okay. Okay. So now we actually want to use this as a possible as answers for the solution. Plug it in to the Einstein equation and solve. Okay, that is what we want to do. That is the rigorous way of obtaining the solution. Okay, but what I'll do today is to get the solution in a cheat way. Okay, and once we get the solution, then we know what to look for, and then we try to get the solution in a rigorous way. Okay, a cheat way is not actually cheat way; it's just a trick way of kind of arriving at the solution, and let's see how it goes. Okay. Yeah, so this is what I was saying. It is useful to kind of obtain using the imposing the symmetries. Okay, so what we want to do is to substitute that form of the metric to determine A row and B row. Okay, Mm, fine. So now what actually happens is that, like, as I said, that these are functions only of one variable, so these equation should reduce to some bunch of ordinary differential equations which are typically coupled and nonlinear, and one is to solve those coupled nonlinear equations. Okay, and besides solving them, they would of course contain some arbitrary parameter, which exactly the way we solved in the electrostatics case. We will determine those parameters by comparing with the parameters of the sources. Okay, in this particular case, we have only single point source. Okay, fine. So as I said, we will kind of follow a cheat way first, and then we'll kind of arrive at the rigorous solution. Okay. Now, I call it cheat way simply because we are not actually going to use general relativity at all to get the solution. What we are going to do is to use two things that we already know, and that is, we know Newton's uh, uh, law of gravitation. We will use that equation, and we know special relativity. So we are going to only use these two and get a solution, uh, or rather form of the metric. I'm not going to show that it is a solution uh, uh, by using this method, but of course we will see that that is a solution. There's one way of understanding why that is a solution, but as once we get the solution, I'll tell you. Okay, so here's the trick. First thing that we will do is to assume that the problem has spherical symmetry. Okay, this tells us that we are going to write down our metric in this particular form. Okay, fine. So this is our starting point. Okay, now remember, we are we are only going to use special relativity, and therefore the metric is in some sense flat. Okay, so therefore anybody who knows only special relativity with spherical symmetry would have written down the metric, spherical part of the metric in this particular form: rho squared times d theta squared plus sin squared theta d phi squared. Okay, without asking any questions. Okay, only thing that the fellow would say is that, like, I need to understand what is the dt squared d rho squared part of the metric, and therefore that fellow may want to write down two functions here. Okay, now besides spherical symmetry, we are also using that the solution, the source is time independent, and therefore these are functions only of rho, something which we have already used. Okay, so that is again something we are going to use here. Okay, fine. So as I said, we are going to use only special relativity and Newtonian gravity. So let's start that. Okay, so let's start with the Newtonian gravity. Okay, so let's consider the gravitational field generated by a point particle of mass m. Okay, we know what that is. Okay, so what we are going to do is that there is a gravitational field produced by this object. To know what is the gravitational field, we need to probe it, right? We have to do an experiment. So let's consider the probe particle, which will sense the gravitational field generated by this point mass. Okay, so let's consider the probe to be non-relativistic. That means, you imagine that you are very far away from the point mass, then the gravitational field is very, very weak, and the particle is moving very slowly. Non-relativistic physics is fine. Okay, so this probe is experiencing the gravitational field generated by the point mass that we are looking at. Okay, so I'm going to use the I'm not going to use this complicated language. I'll just call that source itself to be m. Okay, so that don't keep using gravitational potential due to point particle of mass m all the time. Okay, just to kind of simplify. Now, what we are going to do is the following: that we are going to take the non-relativistic probe particle to have a unit mass. Okay, so small m is equal to 1. Okay, and in addition to that, we are going to assume that if this particle is far away, let's say at infinity, say, okay, then this total energy of that particle is 0. Okay, fine. Now remember, the total energy is kinetic energy plus potential energy, right? Okay, kinetic energy is half mv squared, and potential energy is minus g Newton capital M, which is the mass which generates the gravitational field, times small m upon r squared, right? Sorry, upon r. Okay, gravitational potential, not the force. Okay, so this quantity is equal to 0 is what we want to set, but the small m mass is taken to be unit mass 1. Okay, so let's do that. So that gives us the equation which tells us that half v squared, because small m is 1, half v squared is equal to g Newton times capital M times small m, which is 1 upon r. Okay, this is equal to this because this minus this quantity was equal to 0 because the total energy is 0. Okay, so are you with me on this?
Yes, sir.
Okay, good. So this is one of the equations. Now, please remember this one. I'll write it again, but keep it in mind. Okay. So of course, is v squared is basically magnitude of this v squared. Okay, which is the velocity of the probe particle in the rest frame of the particle which is produced by a particle of mass m. Okay. So we'll call it, as I said some time ago, we'll just call it in the rest frame of m. Okay, which means rest frame of the particle of mass m, really. Okay, fine. Now, left hand side of this is of course kinetic energy, right hand side is the negative of the potential energy. Okay, now let's do the following thing. Okay, this is the non-relativistic Newtonian description of the story. Let's get to the relativistic description. So let's now assign a reference frame to a radially infalling probe particle. So imagine this probe particle is falling in towards the capital M mass particle. Okay, and it is falling in radially. Okay, it doesn't have some impact parameter or something. It is falling straight head, going to have a head-on collision with this object, going straight in radially. Okay, so this one is called a radially infalling object. Okay, and we will call it a radially infalling probe particle. Okay, now we will do special relativity. Now suppose we are looking at two events which are happening at the same spatial point. Okay, but they are separated by time interval delta t0 in the frame of m. Okay, fine. So in the frame of m, we are using x0, t0 kind of coordinates, and they are occurring at the same spatial point in the frame of m. Okay, but they are separated by time interval delta t0. Okay. Now remember that our detector or our probe is infalling radially. Okay, so it is actually moving. We want to use special relativity and ask what is the time interval delta t that infalling probe would see between these two events that occurred at the same spatial point. Okay, I just want to ask a question only about what is the time interval. Okay, I don't worry about anything else. Fine. So the event is at the same spatial point in the rest frame of capital M. Okay, they may not be at the same spatial point in the rest frame of the infalling probe, but I don't care. All I want to ask is that the distance, the time interval delta t0 in the rest frame of M, how does it look like in the frame of freely falling object? Okay, so in the freely falling frame, delta r naught was 0 in the frame M, and delta t is delta t0 upon square root of 1 minus v squared. Is that correct? There is a delta R, but I don't want to look at that right now. I just want to look at delta T. And that tells me that this quantity would be this. Okay. This is just a statement of time dilation. Okay. Is that fine? Okay. So
Yes,
I
sir.
suppose, yeah. Okay. So what we'll do is so the observer who is in the race frame of M, okay, would say that this is how the infalling probe would see the time getting dilated, and therefore he would say that delta T naught in my coordinate system would be equal to square root of 1 minus v squared times delta T in the infalling fellow's coordinate system. Okay, pure special relativity. And therefore, that fellow would say that delta R naught in my frame is 0 anyway, and therefore I would conclude that from the infalling probe particles point of view, the ds squared will be just minus delta T naught squared, which is equal to minus 1 minus v squared times delta T squared. Okay, delta T whole squared. Okay, I should probably put a bracket. Okay, delta T naught whole squared is equal to delta T whole squared times 1 minus v squared. Okay, so that is how the fellow would conclude. Okay, fine. Now let's do a second experiment. Okay, now we are going to do a second experiment where both there are two events which are happening simultaneously. Okay, that means delta T naught is 0, but delta R naught is non-zero. So they are happening simultaneously but separated by distance delta R naught. Again, written in terms of R naught variables, that means it is the whole thing is measured in the race frame of M. Okay. Now suppose you do that, then this the observer in the race frame of M would say that two events happen simultaneously, separated by distance delta R naught. Okay, but that fellow again knows that the probe is falling in, is moving with some velocity v, and therefore the probe will see length contraction, and therefore the delta R seen by in the infalling frame should be like this. Delta R is equal to delta R naught times square root of 1 minus v squared, because length should be contracted in the frame of the infalling probe. Okay, and therefore the observer who is in the rest frame of M would say that in this particular event, the delta R naught would be delta R upon square root of 1 minus v squared, and therefore the metric will be delta R naught squared, which is delta R squared upon 1 minus v squared. Okay. Now, with respect to these two experiments, therefore the observer who is in the rest frame of M would say that the metric seen by the infalling probe should be these two effects taken together. Okay, in addition to the fact that the problem is spherically symmetric. Okay, so therefore the observer sitting in the rest frame of M, whose metric in the radial and time coordinate is this, because he is in the flat space, okay, would appear to be a metric like this. Okay, the observer would say that the infalling observer would see the metric which would appear to be like that. Okay, because dt naught was written as in terms of dt in this particular form, and dr naught was written in terms of dr in this particular form. So when you square those quantities, would take the form like that. Okay, now let's go back to non-relativistic probe particle problem. You get half v squared to be gn times m. So therefore v squared would be equal to 2 gn upon m. So you substitute that, and you get a metric which is 1 minus 2 gnm upon r times dt squared plus dr squared upon 1 minus 2 gnm upon r. Okay. We of course know that our problem should have had the spherical symmetry, and therefore what we will do is that we will add the spherical symmetric part to the metric, and here is the total solution. Okay, this is a Schwarzschild solution. Okay, fine. So what we are going to do is to show rigorously that the solution to the Einstein equation R alpha beta equals 0 by explicitly solving coupled nonlinear ordinary differential equations. Okay, but even without doing any of that, we have obtained this solution by just knowing two facts, that non-relativistic gravitational physics and relativistic time dilation and length contraction physics. Okay, and given the fact that in one particular frame the entire physics was physics of flat space, um, would guarantee that this should solve R alpha beta equals 0. Okay, so in that sense, I really don't have to do this calculation to tell you that this is a solution, but of course, what we will do is rigorously establish that this is indeed a solution to Einstein equation with a point source. Okay, so what I'll do is that we'll in the next class is to set up the problem in such a way that we can kind of essentially arrive at this solution. Okay, the variables of course would be different. Remember, we have A of rho and B of rho, whereas this is written in terms of R, but as you know that these are all just dummy labels. You can replace R's by rhos and so on to get the same answer. Okay, fine. So to kind of prepare the ground for for obtaining a rigorous solution, let's kind of look at this problem from the alpha beta equals 0 point of view, and I'll leave you with this particular exercise that you could kind of do explicitly by substituting the metric answers to be like this: GTT is equal to A of rho, G rho rho is equal to B of rho, G theta theta equals R rho squared, and G phi phi is rho squared times sin squared theta. Take these four components, substitute that into the Einstein equation, and show that you get R rho rho is equal to A double prime. Prime is corresponds to derivative with respect to the argument. Okay, so A double prime upon 2A minus a quarter A prime upon A times B prime upon B plus A prime upon A minus 1 over rho times B prime upon B. Okay, this is one thing, and these are the other components. Okay, that R theta theta would take a form like this: minus 1 plus rho upon 2 times B of rho minus whole thing multiplied by this parenthesis, which is A prime by A minus B prime by B plus 1 over B. R phi phi is not very independent of R theta theta. That is kind of manifestation of the spherical symmetry of the problem. And the only other non-trivial component is RTT. This is R rho rho versus this is RTT. And let me just shrink it a little so that you can see both of them simultaneously. And so you see RTT takes a form something like this. And you can see that these expressions are pretty similar, except for some sign factors at various places. Okay. And what we will do, or what can be done, is to kind of take linear combinations of some of these equations to simplify the expressions and obtain solutions for both A's and B. Okay, so we of course have sufficient number of equations to determine two functions. So in principle should be possible to solve. All other components of the Ricci tensor vanish. Okay, so therefore they do not impose any condition on A's and B's. Okay, so what we will do is next time is to use these set of equations, manipulate them, and obtain A and B as functions. Okay. Now, of course, we won't be able to solve A and B completely because these A and B are obtained in the space where there is no point mass source. Okay. Only the symmetry generated by point mass is being used. Then we compare that with the parameters which define the point mass and determine the coefficients which are sitting inside A and B to get exact answers. Okay, we of course know what the the answer is namely this, okay, with r replaced by rho. So what we'll do next time is basically arrive at that solution. Okay, so I think I'll stop at this point. Okay, any questions?